Okay, so yeah, Dr. Fitri, later maybe before you leave, we can take like a photo or something. Is it okay?
Oh, sure.
Yeah.
Actually, all lectures always always how to say record it, and then
Oh,
we
okay.
even upload it already in our YouTube department. So just in case
Oh,
you
okay.
need the documentation, of course, don't worry. Also,
Oh,
we
okay.
take the picture now.
Oh, yeah, yeah, sure.
We can take
Maybe I share first.
please,
Yeah,
please.
just a minute.
Yeah.
Yeah, maybe we can have everyone switch on the
The
video.
camera, the video.
Yeah.
So, all students, please open your video, your camera for a moment. I deeply understand that you have how to say the issue for the internet quota, yeah. That's why we couldn't. Okay, Rofi, Sipa, Tria, Zaki, Yara, Tufa, and all students. So please kindly open your video. Tria, Sipa, Zahra, Tufatul. All right.
Ibu sebentar, Ibu.
That is the problem for the online learning, yeah. Sometimes.
Oh, yeah, so for today's lecture, while waiting for them, today's lecture, we will talk about the test, and then after that, I will spend a bit more time for the question and answer with the students, maybe at around 8, yeah. By the time you leave, yeah, that time I will spend some time, yeah.
Yeah, that great idea, Dr. Wenda, yeah. Very great idea, yeah. So, Tufa, Zaki, Tiara, quickly. Okay, Azahra, Zaki, where are you? Tiara, Tria, Tiara. Okay, Dita, open the video, please. Open the camera. We need to keep the documentations. Tria di mana? Di jalan atau di mana nih? Tiara, okay, good. Dita, Zaki.
I think some of them may have internet issue. So yeah.
Yeah.
Let's just proceed.
Yeah.
Okay.
Pak Hafid, maybe you can assist us to take the picture, Pak Hafid.
Okay. Everybody, please look up your camera. Sifa. 1, 2, 3. Okay. Should we take another one? All right.
Another 2.
1, 2, 3. Okay, thank you.
Okay, thank you.
All right, thank you very much. So please,
Thank you, everyone. Yeah.
Just
Okay, so yeah, I think it's time to start the lecture. Our last lecture, right? Okay, so yeah, so we come to an end. Today is week 8. So we will look into how we can actually use a certain software to look into the toxicity of different kind of organic compounds, right? So before that, let me just give you an overview of what we have gone through, a more detailed one, right? So in week 1, we look into some introduction. Okay? This is just to remind you what we have gone through, right? So far, we look into introduction, and we also look into what exactly is the purpose of studying environmental toxicology, and why we need to study it. Okay? One of the reasons is because we need to know before we release a certain chemical to the population, whether this kind of chemical can cause a lot of harm to human or even the environment. For instance, one of the cases that I shared with you all is in terms of the thalidomide, right? Thalidomide is one of the drugs that was prescribed to people who have anxiety, right? So this thalidomide drug helps them to sleep well, but unfortunately, it has certain tetratogenetic effect, whereby it affects the fetus, right? So pregnant women who have anxiety issues, they take in these thalidomide drugs, and then they found that their fetus have developmental problems, right? So this is one of the cases whereby we need to study the environmental toxicology of most of the compounds. So there are many different fields in this environmental toxicology. For instance, you have environmental toxicology, you have a forensic toxicology, you have a computational toxicology, and so on. So this is generally a very big area of concern, right? So we also look into risk assessment. If you recall, we look into how we can conduct a very simple risk assessment and what are the things that we need for risk assessment to be conducted, right? So risk assessment basically is required for us to assess the risk of a chemical in the environment, right? So risk, if you know the definition, is actually hazard times the exposure, right? So risk assessment itself is we have to have 4 steps, right, for it to be conducted properly. First is you have to have the hazard identification, so which means that you have to have the data available in the literature or any other proper scientific data, right? So from this data, if you know that it is toxic, then after that you carry out additional steps, right? You carry out those exposure assessment, you carry out toxicity assessment, right? So these two will let you know whether the risk is severe or not severe, right? So if it is severe, then of course you have to report it, okay, in a very objective way. Let people know that this needs to be addressed immediately, right? So sometimes there are cases whereby there's hazardous substances in our environment, for example, mercury in fish, right? But then the exposure level is not so high, which means that, let's say mercury, you need 10 grams to suffer from the effect, but we are only exposed to 1 milligram, right? So you can see the difference here, exposure and the hazardous effects, right? So due to the low exposure, then of course we have to say that this mercury did not pose any problem to us, right? So after that, we also look into dose response relationship in week 2. So in this week 2, right, we look into how we can actually conduct a proper dose response relationship, right? How we can actually get the data and what are the possible response that you can take, right? For instance, let's say a particular toxicant can induce central nervous system damage. So you can actually use the CNS damage as one of the response. So it is not necessarily death as the response. It can be anything associated with the ill effect of the toxicant itself, right? So those response relationship is quite well studied especially in drug. It's very necessary because in drugs, for instance, medicine for people, right, for the population, before you introduce it, you have to have the dose response study, right? So we have to know whether this particular drug, at what dose it will cause the good effect, at what dose it will cause the harmful effect, right? So we have quite a number of ways to do it, right? And then after that, week 3, we look into toxicokinetics and toxicodynamics, which they are part of the so-called toxicity assessment, right? We look into the how this toxicant can be absorbed our body, either through our dermal route, either through our digestion, or sometimes through our lung, right? So these are the 3 ways whereby the toxicant can be absorbed by our body, right? So once it's absorbed, the next thing is it is distributed, right? It's distributed all over the body, right? It can go to your lung, it can go to your kidney, your liver, and so on. And the distribution generally depends on many factors. For instance, if you have distribution occurring in the lymphatic system, then it is lower compared to when you have distribution via blood, right? Blood distribution is very fast because it's a pressurized system, right? So we talk about it. Those organs that receive a lot of blood flow tend to suffer from effects more than those organs that did not receive as much blood flow, right? So there's several studies in USM itself, in the pharmacy school, whereby they look into the toxicokinetics, right? Sometimes when they want to look into this, right, they will prepare let's say a drug, they'll prepare it, and then they will label it with the isotopes, right? Which means that it's radioactive, right? But then it will not be very harmful to our body. Okay? We have designed the drug carefully. And then after that, we let test patient, right? Volunteers eat that drug, and then it goes to their body. And then we use certain equipment to look into how these radioactive isotopes distributed in the body, right? So I know several researchers here who are carrying out this kind of study. So they look into before you eat something and after you eat something, what is the difference in terms of the absorption? And then they also look into, let's say, a particular drug that is useful for the liver, right? So they also look into what is the percentage of the drugs that actually reach the liver, right? So this kind of study is quite common. But then because of the complexity of the study, right? Most of the time they will just engage a company or maybe commercial lab to do this kind of study, right? So we also look into, after distribution, we look into metabolism, right? Metabolism, we have phase 1, phase 2 metabolism, whereby phase 1 is generally more towards oxidation reaction. We want to oxidize the toxicant so that it becomes more water soluble, right? Phase 2 is more towards addition reaction. So we have an enzyme and then we have the cofactor. So this enzyme cofactor can actually interact and then catalyze the reaction of conversion of this toxicant into something of a larger molecular weight, right? So after metabolism, then we have the excretion. So excretion can go through various ways, for example, saliva or our hair, and then we have excretion through our urine and so on, right? So and then we talk about toxicodynamics, whereby we see how those toxicant can induce certain toxicosis, which means certain effects. So we talk about liver toxicity, we talk about blood toxicity, we also talk about the neuron CNS, central nervous system toxicity, right? After that, week 5, we look into mode of action, toxic action, whereby we look into the enzyme, how it can inhibit be inhibited by certain toxicant, and how it is going to cause harmful effect to our body through a more fundamental way. In other words, more chemistry. Then week 6, we look into abiotic reaction, okay? Mainly this photo reaction, right? Concerning those UV and visible light from the sun. So those UV and rays, when it hits a particular molecules, for instance, your organic molecules, you can have excitation. An electron can move from the lower energy state to a higher energy state, and then you have reaction happening, right? So we also look into the transport of this toxicant. Can travel through other places, through wind erosion, through photolysis, through adsorption, and so on, right? So week 7, which is last week, we define differences between genotoxicity, tetratogenesis, mutagenesis, and carcinogenesis, right? So we know the differences in why we actually categorize them differently, right? So genotoxicity is actually caused by something that can cause DNA damage, right? And genotoxicity can be a mutagen, right? And of course, not all carcinogen can be classified as genotoxin. Sometimes carcinogen can also affect the cell through different means. For instance, it can increase the production of hormones and so on, right? So those carcinogen that affects the DNA is in the genotoxin category, but those that are not, is not as classified as a genotoxin category. So week 8, we want to look into how we can do something different, okay, more practical. I hope everyone download this software. It's actually a free software, a very useful software for us to carry out tests, right? A test on the toxicity of a substance, right? So in the environment, right, we have many different kind of pollutant, right? So especially those organic pollutants, right? So the organic pollutant itself can be transformed into many smaller molecules. Sometimes it can be polymerized into larger molecules. In other words, there are many reactions that can happen, right? And because of this kind of reaction that can happen, right, what will happen is that we will have difficulty in estimating the toxicity of different substances, right, different pollutants. So we have to have a proper way, a proper technique, so that we can know, okay, to some extent, or actually predict whether this particular pollutant, if it is degraded in the environment, will the products of degradation be toxic compared to the parent compounds, and so on, right? Okay, so just to share with you where this test software can be used, right? It is actually quite a famous software, right? And the name is Toxicity Estimation Software Tool, right? It is quite well used by many people, many researchers, and most of this software you can see it in publication, right? One example is this paper is published by my group, right? In very recently, about 2 months ago, and we actually use this test software to model the toxicity of the degradation intermediates, right? So yeah, this is quite accepted by many people, right? Because it is by EPA, US EPA. It provides a way to estimate the toxicity, which means that we can use it. We can see whether the product is more toxic or less toxic. It's very simple to use. I will show it to you later, and then we will have a practice section. Okay, I hope you all have downloaded this, so that we can look into how we can use this software to predict certain endpoints, like for instance, toxicity to fish, toxicity, mutagenicity, and so on, right? So in this paper, what we did was we actually take waste, okay, waste like sawdust. Sawdust is actually a waste from the industry, right? We take this waste for free, and then after that we carry out certain treatment to the waste, okay, so that it can be transformed into a catalyst, right? So after transforming it into the catalyst, we use this catalyst to activate a chemical called peroximonosulfate, right? So this peroximonosulfate is very special because it needs to be activated to produce reactive species, right? Yeah. So we use the catalyst to activate this chemical. Okay? We generate the reactive species, and then this reactive species is used to attack the pollutant, right? For this case, we use this gatifloxacin. This is actually antibiotics, right? It belongs to the fluoroquinolone antibiotics, and this antibiotics it is used in several countries, okay, because it is effective, right? And it is known to inhibit the DNA, okay, enzyme DNA gyrase, and also topoisomerase 4, okay, which means that once it enters into the microorganism cell, it can destroy the DNA. Okay? It can inhibit certain processes that leads to the cell death. Okay, so of course it's also banned in certain countries due to its side effect. Okay, but that's not the point. The point is that once this gatifloxacin reach river water, it is going to be causing a lot of harm. For instance, it can cause the emergence of antibiotics resistance microorganisms, right? Or in other words, we call it a superbug, right? So we don't want this to happen. So we have to treat this kind of pollutant, right? We don't want it to be in the environment and cause a lot of harm to us until a point whereby all the microorganisms in that river will not be susceptible to these antibiotics anymore, right? So what we did was we take this GAT, we degrade it, and then after that we look into the different kind of intermediates, right? So these are the intermediates that we found. We inject it into LCMS, right? Liquid chromatography mass spec, right? And we found that this GAT, right, can actually be degraded to many things, Right? We have pathway 1, which means that it is transformed into quinolone moieties. We have pathway 2. Okay, pathway 2 leads to destruction of piperazine ring. And then pathway 3, destruction of chlorophyll moieties. And finally, pathway 4, we have the defluorination. Right. So one of the questions that people tend to ask is that, are these intermediates toxic? Right? Because you have the GAT, right? So after treatment, you can have a lot of different kind of products, right? So if all these kind of products, they're toxic, so the next thing that we have to do is we have to increase the treatment time, because generally what happens is that the GAT is degraded through 4 pathway, and eventually by increasing the time, it will become carbon dioxide and water, right? And of course, time is equals to money, right? So if you increase the, let's say, the treatment time from 1 hour to 2 hours, you actually increase the cost of treatment, right, significantly, right? So if we can actually degrade it into this kind of intermediates, right, and all these intermediates, they are not toxic, then it is actually a good achievement, because we can just release it out into the environment without further treatment, right? So the question is that, are these intermediates toxic? And it's very difficult to look into each of these one by one, right? Because if you want to know the toxicity of, let's say you have P1, P2, P3, P4, right? If you want to know the toxicity of P1, you have to get a standard compound, you have to test it with the, most of the time it is animal study, in vivo study. It's very time consuming. And then if you look into the studies with animals, you have to have ethics approval, which means that you need to prepare a huge amount of paperwork, and you have to wait a long time before you can actually be given the permission to run this experiment. And by that time, a lot of time will be wasted, a lot of money will be gone, right? So we need to find a way, okay, to replace the traditional testing methods. Right? We need to be able to predict all those toxicity. And then, in fact, we through prediction, right, we can identify which one is the most toxic one, and then we can do something about it, right? So for that study, what we did was we just a minute, okay, we carry out the study, and then after that we use the test software to look into several parameters. For instance, we look into the acute toxicity, we look into the developmental toxicity, mutagenicity, and bioconcentration factor. Right. At the first look, okay, for people who are not familiar with the test software, okay, one first look, you will see that, okay, this is very complicated. How can we do this kind of figures? But it is not. It is actually very simple, right? So okay, there are several parameters. Okay, if you look at the literature, they will tell you that if you use this 48-hour Daphnia magna, okay, this is the endpoint, LC50, lethal concentration 50, which means that the concentration that is sufficient to cause 50% of the death. You see that the value here is 0.1 to 1 is very toxic, 1 to 10 is toxic and harmful, and not harmful. So if you get the value between 0.1 to 1, you can classify it under the very toxic category, right? And so on. Mutagenicity, if it's 0 to 0.5 is negative, 0.5 to 1 is positive, right? So for bioaccumulation factor, okay, less than 1,000 is not significant, and so on. More than 5,000 is highly bioaccumulative. Okay. So let's look at how we can actually use this software. But before that, just to highlight that test is actually based on QSAR, right? They use QSAR method. I believe this one you will learn later on, right? What exactly is QSAR method, and what is molecular descriptor and how this QSAR mathematical model actually works, right? So this test actually allows us to use QSAR method to predict the toxicity, okay, without the requirement of external program. Okay, like some software, you need to have a certain external program, link it together, and very complicated. But test is not like that. Okay, test is very simple. Okay, so these are some of the methods that can be used for prediction in the QSA method. You can go through this. It's in the notes given to you, right? You can download it, right? The most common, most reliable one is the consensus method. This consensus method, which take into account all these single mode, group contribution, nearest neighbor method, and hierarchical methods, right? It is actually taking into the average of the predicted toxicity, right? So this is the method that we use for later part. Okay. In terms of the advantage and disadvantages, you can see that here in this table, right? This table, I take this from the manual of the software. You can download the manual easily. Okay, it gives you a good explanation on what exactly is this test software is about, and then it also gives you some theoretical explanation about the QSAR and all those mathematical formulas, and then the molecular descriptor and what kind of molecular descriptor they are using and so on. Right. So this one, I think we will not cover today. We will look into how we can be an end user of the software, okay, by predicting the toxicity, right? Okay, so I'm going to start off with by sharing the software. Okay, let's go to the software. Just a moment.
So, Dr. Winda, before you move to the software, I guess this is the good, how to say, information here for us. But I'm personally very wondering why you prefer to choose the consensus model. Is it much more convenient? Or
no, yes. In terms of the in terms of the predictive power, right? Consensus method is the most accurate one. Because it takes into account the average of the predicted toxicity of all these methods, right? So if you are an advanced user and you know what you're doing, you know what you want to find, you can choose either you want to use a single method, you want to group contribution, or any other different methods. But the error is larger if you don't know what you are doing. So for people who are beginners, like myself, I don't consider as an advanced user yet. I will use the consensus method simply because it gives better prediction in terms of the numbers. It is also if you compare with other methods, more reliable, right? So there's a validation part. Okay, I will not cover in this talk, but then just to brief you all in terms of the validation, right? You can look at the manual. Okay, there's a manual about this book whereby they have validation of the results, right? So you can go through, and generally what it says is that all those methods, they are validated, and the consensus method gives you a better predictive accuracy compared to others, unless you know what you're doing, and unless you know the molecules is actually better model using, like, let's say, single model methods, then you can actually use that. There's no right or wrong in terms of choosing, but then for beginner, consensus method will give you a more accurate prediction, and is much more reliable. That's my take, right? So I personally use consensus method to predict the toxicity, because all those other methods, because what I'm doing is that I have a different kind of intermediates, right? So because there are so many different kind of intermediates, it's very hard for me to select. Let's say one, I want to use single model methods, one I want to use the nearest neighbor methods. Yeah, so to make it more reliable, I choose consensus method. Yeah. Okay, so there are advantages and disadvantages as what you can go through. Yeah, you can see the consensus method was shown to achieve the best predictive results. Right, but of course there are certain issues in terms of the disadvantage, like cannot provide external estimates of the toxicity of a compound in the training set. But of course, this is just an average method, right? Okay, so let's go to the software. Let me just share it. Okay, yeah, so this is how the software look like. Okay, just a minute. Okay, so you look at this software when you download it, right? You look at it, it's very simple. It's not really very complicated, right? You have several columns, several areas whereby this part, this you can see my mouse, right? Can you all see my mouse? Okay, so you have to enter a CAS, smiles, name. This is the part whereby you enter your molecules, right? You can put in benzene, you can put in any different kind of molecules here, right? And then you have the calculation option. Okay, calculation option is when you want to set up certain parameters. So endpoint here is what kind of test you want to use. For instance, you can use Daphnia magna, LC50. Okay, this is the test of using this organism and then conduct it for LC50 test, right? Then you have the oral rat, LD50, bioconcentration factor, developmental toxicity, mutagenicity. In fact, you also have certain physical parameters, for instance, normal boiling point, vapor pressure, melting points, flash points, and so on, right? You can actually predict all these different physical parameters using this software, right? For this case, right, we are interested in only these parts, right? Mutagenicity, developmental toxicity, right? So generally, mutagenicity means that you are using this Amos test, right? Which we covered last week, right? So we talked about how a particular toxicant can induce mutagenic effect to bacteria, right? So this bacteria initially it cannot grow, but then after being exposed to mutagen, it can grow excessively. So this is the test that this software is using, right? Whereas all those LC50, LD50 is looking into the lethal concentration that can cause 50% of the population to die, right? So you can look through this. This is the explanation. When you download the software, you can see all those explanation. What exactly is the parameters about? Okay, so let's say 96-hour fat hit minnow, LC50. It means that the concentration of the test chemical in water that cause 50% of the fat hit minnow to die after 96 hours, right? And all these, they are the description. Okay, it is a very user-friendly software. Consensus, okay, method is my method of choice, right? Because it takes into account all these other different kind of methods used for the QSAR prediction, right? So you have the nearest neighbor, group contribution. You can see that they are actually providing a description here, right? So the consensus method is the one that I feel should be used by beginner like us, right? The predictive toxicity is estimated by taking average of the predictive toxicity from the above QSAR methods, right? All these different methods. Okay, so right. So this one, fragment relaxed fragment constraint, we don't have to touch it. There's no issue with it. This is actually, if you're using different kind of methods, then you may want to use this. But if you're using consensus method, you don't have to check this relaxed fragment constraint, right? You have the explanation over here, right? This is more towards the fragment of the test chemicals, which is not of our concern. And then for this run CTS, you can click here. This is actually more towards the web-based tools, right? This one, we don't have to check this also. Then the select output folder, you can select where you want it to go. And then create detailed report. You can, if you want to create a detailed report, you can do that. Okay, you can save it at the output folder, right? And this part on the right-hand side, you'll see that there's an option, okay, whereby you can draw chemical, right? So when drawing chemicals, you can have several choices. You can actually draw it here, okay, in this software itself, okay, which means that you don't have to import it from other places. Or sometimes you prefer to draw it in another software, maybe like ChemDraw, right? You can do that. You can use the software in ChemDraw, and then you can draw a structure. right? And then after that, you can import it to the test software. Right? So if you look at this part, switch to batch mode and calculate, right? Usually I will not use this is what we call as a single mode, right? Single mode is longer, it requires longer time, and it is used for different purposes, right? Sometimes if you want to predict the pathway and you want to know the toxicity of the degraded products, right? Sometimes you can use this single mode. You can make prediction, but if you have the data itself, right? Usually I will not use this single mode for the reason that it takes longer time. Okay, it can take very, very long time depending on the computing power. Sometimes it takes like half an hour, sometimes 1 hour. So we'll not use the single mode, we'll switch to batch mode. So usually I'll click this. Okay, so this is the batch mode. Okay? And batch mode, you can have the selection of the chemical, which will show in the right hand side later. Let me just show it to you. Okay, let's say for instance we want benzene, right? We can just type the benzene at the column at the left side, okay, benzene, and search. Okay, and you see here you have the benzene coming out, which means that it is in the system, right? If we don't type benzene, let's say we type something that is wrong in terms of the spelling. Okay, let's say that I have a typo here. I press search. Okay, you'll see that it will tell you that benzene not found. Okay, the identifier, it is not found. The molecules that I key in is not found because it is not available. So this software will identify the chemicals for you if you know the name. Okay, so once you know the IPAC name, you just need to key it in, and then it is very fast. Okay, straightforward. It tells you the chemicals, and then from here you can use it to carry out your toxicity assessment. Okay, let's say I delete this. Okay, let's say you don't know the name. If you want to draw chemicals, right? You know the structure you want to draw it. You can click draw chemicals. Then it will come out this screen over here, right? And then you want to know what is let's say benzene, right? You want to know the benzene toxicity in the system. You just need to draw it yourself. You can draw it by line, or you can just click here. Okay, it gives you the ring. Okay. Let's say if you have extra things, instead of benzene, you have a certain OH group, make it into phenol. Then you can click oxygen at the lower part. Yeah, this is a phenol molecule, right? So you can draw any molecules that you want. Okay, and then it will it will show you in the screen later. Let's say this is the molecule that I want. I click OK. Do you wish to update the CAS? Yes. Okay, so this you can see the system identify a molecule as phenol. I did not write anything about phenol, but then the system automatically know that the molecule that you draw is actually phenol. So it comes out here in this. Okay. So let's say you want to use other software. For instance, you want to use ChemDraw to draw it, and then you want to place it here, right? So you can do that. Okay, let me just show it to you. Okay, so this is a ChemDraw, right? You have the ChemDraw over here. It looks like this, right? So let's say you want to draw a chemicals, for instance, you want to have a naphthalene, right? Naphthalene, you have this, and then you have okay. Sorry, my drawing is not so nice. Yeah. Okay, so if let's say you have these chemicals and you want to know what is the toxicity, and you want to export it to the test software, right? What you can do is you can select this molecules, and then you go to edit, and then you copy as smiles, right? So once you copy as smiles, you can go back to your software. Okay, let me just go back to the. Okay, so you can go back to this test software, and then you can paste it, okay, in this area over here, okay, and then you press search. And then you see, number 3 here, you will have the naphthalene. Okay, it will show you that you have these chemicals here, right? So it's quite flexible, okay, and it depends on whether you want to use this test software to directly draw your chemicals, or you want to use the ChemDraw to do it. So sometimes I will use ChemDraw to draw because it is much simpler, especially when you have a lot of different kind of molecules, right? With a lot of intermediates, right? So using ChemDraw to draw for me, it's much easier to do it. And then you can select the structure one by one and then put it into the software here. Okay, and this left side, right? So you can draw and you can insert the names. It's also okay. It will not affect the results. After that, you go to the calculation option. Okay, calculation option, you have endpoints, right? Whether you want to have it as this Daphnia magna LC50, you want to get a bioconcentration factor, developmental toxicity, or mutagenicity. So developmental toxicity means that we want to see whether this chemical can affect the toxicity of the and developmental of the organism. Okay, in other words, the toxicity will induce developmental problems. And then we have bioconcentration factor, whereby we are looking into how these chemicals can actually be accumulated in the body of the fish, right? So let's say for this case, we'll look into mutagenicity, right? We select mutagenicity. Method-wise, we select consensus, right? And then we select all the chemicals, and we press calculate. Right? So once you press calculate, you get the results. You can see you need some time for the calculation to run. So the more chemicals you have, sometimes it takes longer time. Okay. So for this case, if you look at this is the results, right? Sometimes it's negative, right? Mutagenicity negative. So you have Na. Sometimes you can see that there's no value. One of the reasons why it has no value is because the data is not available, or maybe the prediction has certain problems. Right. So this is for mutagenicity, right? So if you want to look into let's say LC50 for this Daphnia magna, right? We can calculate again. So you can see the value, right? Benzene, the predicted value for the LC50 is 26.26 milligram per liter, whereas other chemicals like naphthalene, drawn structure is 7.42, right? So that's the difference in terms of the values, right? And then the other one is phenol. Phenol is 7.44, right? You can see the difference, right? So generally, all this value shows that 26.26 is higher. So that means you need higher dosage to cause 50% to die. So that means benzene is relatively less toxic compared to when you have naphthalene or you have phenol, right? So in terms of interpretation, it depends on us. We are the one who interpret the results. So this software can only give us the value itself, right? So let's look at the chemicals that I have. Okay, just a moment. Okay, so in the slides, we look into a chemical called gratifosacin, right? So I know the name, I paste the name here, right, in this software. I press search, then it gives me the gratifosacin, right? You can see here, this is the the chemicals, right, with the formula given. So when you see this, there's no error, right? That means that this compounds is registered with the system, right? Is in the library. So all you need to do is from this gatifosacin, you press calculate, and then it will give you the value. I give you the value of the LC50. And for this case, the gatifosacin is 19.77, right? So for, let's say for my slides, right, I look into acute toxicity. Let me just share back. If you look at the value here, right, it is 19.77, right? Okay. So now I'm sharing the PowerPoint slides, right? Just a minute. Okay, so just now we look at the toxicity LC50 of the gatifosacin, right? And the value that we get is 19.77, right? So that 19.77 is this value over here, right? This is the GAT, right? And then this is 19.77. Right? So if you look at the intermediates, we have a lot of different kind of intermediates like P1, P2, P3, P4. Right. So if you look at the scale over here, we actually have P1, P2, P3, P4, P5, P6 until P15, right? So all these correspond to the intermediates, right? So each of these intermediates, we know the structure, right? So because we know the structure, we can actually draw it using ChemDraw or using the test software directly. So after drawing that, we calculate what is the LC50, and then let's say the P1, right? P1, the LC50 we calculated, and it is around 90, right? So we will put this bar over here, correspond to P1, the toxicity of P1, right? And then P2, P3, P4, we also do the same thing, and then we will be able to see at what level the toxicity is. Okay? And then we can compare with the original compound at the beginning, right? So if you look at this, right, P1, P2, P3, P4, P5 have a higher LC50 compared to the GAT. Okay, this means that pathway 1 leads to relatively non-toxic, okay, or less toxic intermediates, okay, because they need higher concentration to induce effects to the organism, right? Whereas if you have pathway 2, pathway 3, pathway 4, okay, you can see that for GAT, right, it is here, but then all those other intermediates, they are at the lower side, okay? Which means that they are more toxic because lower concentration is required to cause effects to the organism, right? So this is how we can look at the data. We carry out the degradation, and then we look at the toxicity, and then we compare with the original compound, right, to see, okay? And then after that, we can deduce that out of these 4 pathway 1 leads to non-toxic intermediates, pathway 2, 3, and 4 leads to more toxic intermediates, right? Of course, some of the people may ask, okay, if pathway 1 is the one that leads to less toxic intermediates, why not we just do pathway 1? Why not we skip all those pathway 2, 3, and 4? The answer is very simple. It's because it's very difficult to control this kind of reaction, right? If you have a molecule, right, and then you have nucleophile and electrophile, right, they can attack everywhere, provided that that particular area has affinity for that kind of either nucleophile or electrophile. So that's the reason why we cannot control a certain pathway. All this pathway can happen. Then there's a probability whereby pathway 1 can happen, probability whereby pathway 2 can happen, 3 can happen, and 4 can happen, right? The larger the molecule you have, the more difficult you control the reaction site, right? Smaller molecule, of course, you can control easier. You can actually design maybe an electrophile or nucleophile that can attack that particular group. But then the larger molecules, you have more active sites. you have more electrophilic site, you have more nucleophilic site. So it makes things more complicated. So for this case, it's very difficult to control at pathway 1. All this will exist in the degraded solution, right? So for this case, we can make a conclusion based on the accused toxicity prediction that some of the intermediate may be toxic compared to the original compound. And for this case, it's very difficult for us to stop the treatment halfway. We have to carry out the treatment until all these compounds has become carbon dioxide and water. Okay, that's the conclusion we can make. Aside from the acute toxicity, we also have developmental toxicity, right? Which means that we select a different endpoint, and then we can see the values will tell us what is the level of toxicity in comparison with the beginning, okay, with the parent compound. Okay, so in the chat, we have one question, how the intermediate compounds can be obtained. This one we have to do it experimentally. Okay, experimentally means that, okay, for this case, for my case, all these compounds, I use LCMS to identify them. Okay, so generally we start out with GAT. Okay, this is the beginning, okay, the beginning of the reaction. We have all GAT, right? And then after that, we carry out the reaction. And then after 30 minutes, let's say the reaction time is 30 minutes. After 30 minutes, we collect the sample. And then after that, we inject the beginning, okay, the initial sample and the final sample after 30 minutes into LCMS. Right. So after that, we look at the difference, right? So LCMS in the beginning, you will see that there's only a mass spec corresponding to GAT. Okay? You will see GAT peak only. But then after 30 minutes, you will see that there are many different kind of peaks, okay, ranging from P1, P2, P3 up to P15. Okay? You'll see all these intermediates, right? So that's how we determine the intermediates, right? Through using LCMS. And after getting the intermediates, right, then only we proceed with the toxicity test. So in other words, you have to know what this molecule can be transformed into before you can carry out toxicity assessment. And for our case, right, you can see we have 4 pathways. So this 4 pathway is not the only pathway, you know. There could be more pathways, pathway 5, 6, or 7. But then because of our the limitation of the LCMS, sometimes we cannot detect all those additional pathway. So these are the pathway that we identify as the major pathway, pathway 1, 2, 3, and 4, right? So generally we use LCMS, and then after we get the intermediates, only then we carry out the toxicity study to assess whether they are more toxic than the parent compound or less toxic. Okay, so far, any questions from everyone?
Dr. Wenda?
Oh, yes.
Yeah, thank you for your explanations. So regarding to the pathway that you set on your study,
Yes.
yeah, even we can set until other pathways, but is this pathway relates to the, how to say, metabolism phase that you
Oh, yeah.
in
Yes.
previous lectures? Yeah, for
Yes,
phase 1 or phase 2, is it related? Okay.
For this pathway, yeah. Okay, generally this one is like when we want to carry out treatment, right, of this pollutant using the technology that we have. That's this paper. This paper we talk about the catalytic technology. So if you want to use this catalytic technology to remove GAT, okay, this chemical from water, right? So what will happen is that this kind of catalyst will cause this GAT to be degraded to all these kind of pollutants, toxicant, okay, or intermediates, right? So generally this is what it means. We have the parent compound, it is degraded into all these intermediates. And then when we have these intermediates, we don't know what is the toxicity of all these intermediates in the water. So we can predict it using the software. So it's the same for metabolism. Okay, let's say you have GAT. Okay, you ingest GAT as antibiotics in your body, right? And then this GAT, it goes inside your body and it can have metabolism. Maybe you have a phase 1 metabolism, phase 2 metabolism, whereby you have addition reaction and all those kind of different reaction, right? And then it will give you a different set of intermediates, right? So the different set of intermediates, let's say something like, right, can actually be used in the software, and we can actually predict the toxicity of all these different intermediates. All you need to know, okay, in predicting the toxicity using the software, the test software, right, is the structure of the molecule. Okay? Regardless of the pathway that you have, the mechanism or anything, it doesn't matter. The important thing is that you know what is the so-called structure of the molecule. I hope I answered the question.
Yeah, thank you. Clear now. I understand. Yeah, thank you.
Okay. So yeah, just to give you a fast guide of what we have talked about just now. Just now we look into how we can estimate the toxicity using the software, and usually I will use the single mode method, right? Because it's much easier. And then in terms of copying the structure, usually I will use the chem draw, because I can actually draw all those intermediates first. You can see from here, right? You have the intermediate 1, 2, 3, and 4, 5, 6. Okay, all those intermediates. It's easier to have this kind of illustration before I copy it to the software, right? So you need to copy as smiles. Then after that, you paste in the software over here, and then you press all those endpoints that you want. For instance, LC50 for Daphnia magna. Methods, I'll use consensus because it's the most accurate one, and also it's the average. It takes into account the average. Okay. And then after that, once I put all the intermediates inside, I select, and then after that, I will get all this here and this part. Okay, so you can see there's no error. So that means all those chemicals, they are acceptable, right? So I will press calculate, and I will get all the values over here. Okay, easily get all the values over here, and these are the results. Okay, we can actually repeat it for mutagenicity. We can repeat for other things, right? So just to highlight the test software where it has been used. So if you look at the paper, right? Okay, or you go to scientific journals, okay, maybe Science Direct, right? You search toxicity estimation software tools. You will see a lot of articles coming out showing you that they use the test software to predict toxicity. And most of the paper I see is quite recent. For instance, this paper, CEJ, right, also published in Chemical Engineering. This is quite a good journal, right? Impact factor is 16 point something. This is published by a group from Iran. They look into how they can assess the toxicity of this chemical, cefixime, right? What they did was they used this photocatalytic reaction. Okay? They use this photocatalyst, right? And then they use it to degrade this cefixime chemical, right? So after degradation, they use LCMS and GCMS to determine the intermediates. Okay, they found that all these are the intermediates. Okay, you have C1, C2, C3, C4, up to C16, right? There are many different kind of intermediates, right? So in your LCMS, right, what you will have is just the structure of the intermediates. Based on the structure, you need to be able to come out with a pathway, right? So in terms of coming out with a pathway, you have to look at the possible group the reactive radical will attack, right? For instance, let's say you have a phenol, right? Let's say you have a phenol, okay? And this phenol, right, is a molecule that contains OH group over here, right? So let's say you have another hydroxyl radical, okay, want to attack this phenol. What will happen is that some of this autometa para group will be attacked by the hydroxyl radical, right? Maybe it becomes something like this, right? At this part. And then after that, further oxidation, you have ring opening reaction, and then maybe you have maybe a smaller molecular structure, right? So based on the LCMS, you will see that you have this 1 and 2 there, right? And then from the 1 and 2, the next step that you want to do is to come up with a pathway. So the pathway you have to propose it yourself, right? You have to use logic. Okay? You know that phenol cannot directly become 2. It has to undergo oxidation first, which is 1, and then only it becomes 2. So this is the step, okay, that you have to propose. So once you have proposed this pathway, the next step that you need to do is take this molecule and then put in the test software, right? And then from there, you can estimate the toxicity. And for this paper, since they identify 16 intermediates, the next thing is they use the software, test software to predict the toxicity. Okay, you start off with this cefizim, and then look into LC50, right, of different intermediates. You can see C6, C15, C1, C16, all those intermediates, they have a higher toxicity compared to the cefizim, right? So that means they are more toxic. So there are many ways to present this kind of data, right? The values that you get from the software, you can actually present it using this kind of figure, or you can use the one that I showed you just now, right? Regardless of the way you present it, they all give you the same results, right? So this is another paper, also in this year, 2022, okay? Published in very good journal also. I think it's Journal of Hazardous Materials. From here, you can see that they also look into acute toxicity using different endpoints, right? And this is all done by the test software, right? So you get all the data, and then after that, you can discuss why the parent compound is less toxic compared to the other compounds, okay? So another one study also by Chemical Engineering Journal. This one is on the ferric ion sodium bicarbonate phantom light reaction. They look into the degradation of this metronidazole, okay, this molecule over here, and then they use LCMS to determine what are the intermediates. And they found up to 5 intermediates, 5 or 6 intermediates, right? P1, P2, P3, P4, P5, right? So after that, they carry out the test analysis, okay, oral rat LD50, one of the endpoint in the software. Then we have the bioaccumulation factor. In other words, can be bioconcentration factor. Then we have developmental toxicity and mutagenicity, right? You can see this is how they present it. Quite different from what I have shown you just now. Some people prefer to use a table, some people prefer to use this kind of figure, but generally they are almost the same, right? Okay, so now what I want you to do is to use your software to start to look into the scheme 1 and scheme 2 toxicity, right? So this is like a practice for us. So let's say scheme 1. Maybe I will just go through this quickly with you, because we need to have a time for question and answer, and it's already 9:05, right? Let's say let me explain how we can actually use this software. Let's say you have a scheme 2. Okay, let's start off with scheme 2. Okay, so from scheme 2, you want to know, okay, what is the toxicity of this polycyclic aromatic hydrocarbon? What is the toxicity of arene oxide, PAH quinones, and also cis dihydrodiols, right? ABCD, okay, in scheme 2, right? So you look at the scheme 2 here. This is a reaction in the liver, right? This is generally how our liver can metabolize the polycyclic aromatic hydrocarbon. In other words, this is a PAH, right? One of the known cancer-causing organic compounds, right? And when it enters into our liver, you can have enzymes oxidizing it. You can have, let's say, enzymes causing it to become quinones, or maybe dioxygenase causing it to become cis dihydrodiol, right? So we have a lot of different kind of reaction happening, right? These are not just the reaction. Actually, this is quite long line in terms of reaction. You still have a lot of different kind of reaction. So I only talk about up to here, this part, right? Scheme 2. Okay, let's look at how we can actually look into the toxicity. Okay, so that we can understand a bit better, right? Let me share the okay, so what we have here is 4 different compounds, right, that we want to study. And then the next thing is we want to know what is this toxicity of polycyclic aromatic compound. I will press draw chemicals, right? And then after that, I will draw the chemicals out. Okay. So if you look at the software, right, I have drawn these chemicals. Okay, I've drawn the first chemical, PAH, and then I press OK. Do you wish to update? Yes. Then you have the first one. This chemical is also called as autoxylene. Okay, so after that, the next chemical that I want to look into is let's say pH quinone. Right, so I will draw chemical again. And okay. Do you wish to update? Yes. So you can see here in the batch list, you have 2 already, O-xylene, 1,4-benzoquinone. And then let's say iron oxide, I want to draw it. Let me just quickly go draw it. So you can see you don't have to draw it perfect. Okay, so you can just draw it. Okay. Sometimes it has a certain problem, right? So this is the reason why I not so prefer to use their drawing software because of these issues. So sometimes it's very hard to draw. Okay, so this is the chemicals that the compounds that we have, like iron oxide. Let me see whether it works. Okay, so we have the three, let's say we only want three, right? Or maybe we'll just look into the last one, right? Last one is the more difficult to draw one.
Dr. Wenda, are you
Yeah.
perhaps opening other windows?
Oh yeah, I'm actually drawing the chemicals in. Can you all see these chemicals that I draw?
No, no.
No. Okay. Let me just get it back.
When you share screen, perhaps you can set it to your
the monitor one. Yeah.
Yeah.
But can you see now the test software?
Yeah, I can see the test software, but not the chemical
it's
structure.
okay. In that case, okay. So I have done with the structure. Okay. So for now, if you look at this batch list, right, you'll see that you have four different kind of compounds which correspond to the compounds that we have just now, right? So after that, let's say we want to study, okay, what is the oral red LD50? We can go to this endpoint, set consensus, and then after that we calculate, right? So you will get the value of the calculation, and it will take some time. Okay, so can you see the prediction results? Can you all see the prediction results?
Yes, we can.
Okay, yeah, that's good. Okay, so this is the predicted results of the four different intermediates that I showed you just now. Okay, so you have from these predicted results of these chemicals, which can be used to model the toxicity of this through LD50. Okay, so this is how we solve it, solve this toxicity issues. Okay, so I think that's all that I want to. Let me just share back the. Okay, so I think that's all that I want to show in terms of getting the toxicity of scheme 2, right? So generally, just to recap back on what exactly this software, how exactly this software can be used is that we have to identify what are the intermediates. For instance, in scheme 2, you have A, B, C, D as your intermediates, and then after that you take the top test software, and then after that you draw the structure in test software. Okay, so once you have drawn the structure, you can select your endpoint, whether you want it to be LD50, you want it to be mutagenicity, you want it to be maybe bioconcentration factor. It depends on you. And then after that, you click OK. It will show you the results. It will give you the values that you can use for comparison. So for example, the comparison is something like this, whereby you first start off with the simple chemicals, and then after that you have the intermediates. For instance, this case, after 60 minutes of photocatalysis, right, you have all those intermediates over here. You can see that you can compare. Okay, compare mutagenicity of product 1, 2, 3 versus the original compound. Okay, so this is how we can use the test software. And one of the assignment, okay, for the last assignment that I passed to you all, the students, is related to this toxicity estimation using test software, right? So you can try it out, okay? Try to download it and try to get it to run. So if you cannot get this software to work properly, you let me know, okay? I will try to find a solution for you, right? So sometimes installation may be a problem. Sometimes the window that you have may be a problem, right? So if that's the case, right, if it's because of the computer issue, perhaps you can try to seek your friends' help to get a computer that can run this software, right? So this software is very useful, especially when you want to estimate toxicity, whether you are in the environmental field or maybe you are in the pharmaceutical field, whereby you want to look into how the intermediates of the particular compound can be transformed and whether they can induce toxicity or not. Okay, so I think that's all from me today for this topic. Okay, and I will maybe have a discussion with the students to see what questions they want to ask. You can ask any questions, maybe related to the first lecture or second lecture that you are not so familiar with, and I'm open for discussion with you guys. Right. So thank you. Yeah. Any questions?
Okay, thank you, Dr. Wanda. Any question from students?
You can type if you have any questions. You can type.
Yeah, you can just put it in the text box, chat box. That is actually very interesting. I should try that at software sometimes. I actually work with I actually work with QSAR, right? So
okay.
Yeah, so I really should try that. But it's not a general QSAR software, right? It's specifically for toxicity.
Yes, that's right. This is just specifically for toxicity.
I see. That should be a good comparison.
So the students are maybe they are thinking of what questions to ask. So yeah, anything is okay that you can ask from.
This last lecture is more like a review for all of the lectures and apply it for on the software, right?
Yeah.
So if you have any question, not just on this lecture but also on the other lecture, of course you can always ask in Bahasa Indonesia, and I will translate it to for you.
Yeah, I can understand also because it's very similar to.
Because Indonesian is actually based on Malay, so yeah, like more the grammar structure is very similar. Most of the word is also same, right? Just a bit different in pronunciation. Adani or Rangga, perhaps you have a question?
Well, yeah, you are giving them stress.
Yeah, because they're my students. I plan for them to work with QSAR, so perhaps they have questions. Tria, come on, Tria.
But generally, this software is more very user friendly, more towards the end user. So one may not know much about QSAR, but then they can actually use this software and directly compare the toxicity of different substances, right?
I see.
So for me, right, my QSAR knowledge is very limited. I know the basics, but not to the advanced level. But then I found that this software can actually help me in terms of getting the toxicity values, okay, for comparison without knowing much about QSAR, which is very good.
Basically, you're like a racer that can use the vehicles but doesn't understand how the vehicles
yes.
work, right?
Yeah.
Any question from student? Oh, I don't think there are any questions. I really hope that is because you have delivered all of your lectures very clearly. Okay, because there are no question, I think we can close for this session.
Okay.
Yeah. So Dr. Wenda, on behalf of Dr. Fitri and our whole department, I would extend our greatest gratitude to you for delivering this amazing lecture series. This has been a very interesting half semester, and I really look forward to see you in some other occasion. Thank you, Dr. Wenda.
Thank you. So and thank you so much for your kind words. Just to close today's last lecture. So I'm very thankful for UPI for giving me this opportunity to talk about toxicology and to give lectures to the students. And also, just to remind the students, you still need to submit an assignment, the last assignment, by the 1st of November. And in terms of the presentation, I saw that almost all the students have submitted, which is very good. I'm very happy to look at it, and I screened through some of the presentation and they look very nice, right? Well done. And then I quite enjoy some of the presentation. So thank you so much for taking so much time to do all those presentation, and hopefully the assignment is okay for everyone. Since today there's no question asked, right? But I hope that everyone can understand that the assignment, and then you can answer them well. Okay. And then also, if you have any further questions, maybe follow-up questions that you want to ask personally, so you can text me directly through my WhatsApp, or you can just email it to me. So I'm happy to respond to you. So usually, if you ask me a question, I will respond it almost immediately, right? So I think that's all from me. So thank you, everyone.
Thank you, Dr. Wenda. See you.
Yeah, see you.